Welcome to Cryptography and Hardware, fourth session. Today we learned something about stream ciphers. You may have learned it before in other lectures, like Introduction to Cryptography or something. And then we specifically look at one example, Trivium, which is a well-known stream cipher, and then we see how we can implement it on VHDL or using VHDL, and then also put it on our FPGA and then check how we can actually communicate with the framework of the board and send, for example, some inputs like the key and IV, initialization vector, and then how we can get the key stream. Good. Some of you have learned already, some not, but yeah, stream ciphers can be actually seen in this category. Yeah, that you have cryptography, cryptanalysis, and cryptography, and then another one inside the cryptography you have protocols, you have asymmetric ciphers, and you have symmetric ciphers, and then inside this category you have block ciphers and also stream ciphers. Yeah. And it was invented somehow in 1917 by Gilbert Bernam as the first type of the stream cipher and the concept. The difference between block cipher and stream ciphers should be well known to you if you have learned this concept before, but as a reference, I just repeat this. In the block ciphers will receive a block of bits, for example, B bits, and then generate another block of outputs as a ciphertext. Means that here you have the plaintext and here you have a ciphertext if it's in encryption, and of course you have a key, which is given to the cipher. But then you cannot give less than, let's say here, B bits. Here, but this is different in the stream ciphers, and every bit individually is given to the cipher, and then one output bit is given. And then how do we actually build the encryption and decryption? We just XOR the output of the stream cipher with the plaintext. This is the concept, and of course the receiver should have the same stream cipher and with the same key and generate the same key stream and XOR it with the ciphertext that you send, and then by XORing, then you receive the plaintext or calculate or receive by XORing you obtain the plaintext. Yeah. This is what I have already explained, that everything is modulo 2 or XOR, and encryption and decryption works the same way. Yeah, and everything is just a single bit. There's this XI and YI, which are the output of the encryption and decryption. They are all just single bits. And then you can have this Y over insecure channel. Transmitted, and then it should be actually okay. There are two concepts, synchronous and asynchronous stream ciphers. And the security of a stream cipher actually depends entirely on the key stream, this key stream that we generate here as I. And this should be fully random. Random, there are different definitions of random. For example, you can say it should be uniformly distributed, means that the number of ones and number of zeros should be roughly the same. But this is not the only criteria, because you can easily generate something which is random, uniform, but it's not random enough. And also must be reproducible by sender and receiver, not by someone in between, but both sides should generate the same stream. And the synchronous stream ciphers, in this case, the key stream depends only on the key and also on an initialization vector, which we call it IV. In asynchronous stream ciphers, the key stream depends also on the output or ciphertext that we generate. Means that this also depends on the input, the plaintext, and here this is ciphertext, and this affects also on the stream which is generated. Then this means that if there is a single bit of error in the communication, this actually propagates. But in the in the synchronous stream ciphers, this is not the case. If one single bit of the key stream is faulty, then only that ciphertext bit is affected. Good. This is, I think, is very clear to you, but as a reference, why modulo 2 or XOR is a good encryption function. Yeah. For perfectly random key stream SI, then each ciphertext output bit has a 50% chance to be 1 or 0. No? I mean, statistically, it's good because you look at the output and this modulo 2, and then if the key stream is random, this randomness is completely transparent to the output, and the output will be also with the chance of 50% 1 or 0. And at the same time, you can reverse it easily, yeah? But by X or S, this, when you call it Y, which was the ciphertext X or S is also X. Yeah? So it's trivial and known to you, I guess. Now, what we said that we need to generate a random pattern on a random stream as a key stream, and one solution is to use random number generators if you are able to reproduce the same at both sender and receiver sides. And in the random number generator field, we have some definitions, for example, true random number generators or TRNG. We have pseudo-random number generators or PRNG, and we have also cryptographically secure PRNGs. Yeah, means that not all of them you can use as a stream cipher, but some of them you can use for other applications. I mean, you should actually know that random numbers play a very important role in cryptography for protocols, for example. If somebody wants to communicate with another party, some protocols need some random numbers to be generated at both sides, but completely independent of each other. They should not be the same random. Yeah? For example, Diffie-Hellman key exchange protocol that you have learned. Yeah? You need to generate random. And these TRNG and PRNGs are actually enough and good for that purposes, but not to be used as a stream cipher. No? For example, the true random number generators, I'm not sure if you have heard of. TRNGs are devices of concept that they are using some physical characteristics to generate some random data. Have you ever heard of A to D, analog to digital converter? I mean, it converts the analog voltage, yeah, the value of the voltage to digital, and usually one bit of them, I mean the first bit, the least significant bit, no, is affected by noise. No? And if the environment has noise, and you take that bit, then it generates a random stream for you. But of course, there are criticism about that. I mean, this is not fully random because it depends on the noise. If there is a periodic noise on the system, then this also affects exactly this stream that you generate by TRNG. Yeah? But there are many different ways, and there is a field of research of defining and developing TRNGs, and there are already TRNGs in many microcontrollers that you use. Yeah? For example, some ARM processors or some other products have really TRNG inside. Now, then TRNGs, you may say, okay, if we have TRNG and they are good, why do we need actually other random number generators like the PRNG? Yeah? The TRNGs are good if they are good, no? But they are slow. The speed that the TRNG can deliver and generate random stream is much lower compared to PRNG. The PRNGs you can build by normal hardware that we are learning, no? like a VHDL Verilog, and then you can generate random stream with a very high speed. For example, if your circuit allows you, then for example 500 megahertz, you can generate 1 bit per clock cycle that fast. You know? But TRNGs are usually not able to generate 500, with a speed of 500 megahertz or 500 megabits per second. This is, I would say, almost impossible for TRNGs that are available now. As I said, the uniformity is not enough. For example, this is one example for predictability. For example, if you have 1, 0, 1, 0, 1, 0, 1, 0, when this is random, but from which perspective? The uniformity is good. 50-50 is not balanced. Sorry, it's not imbalanced, it's balanced. And what is predictable? If you are interested, you may search for NIST test. NIST is NIST, National Institute of Standard Technology. There is a there's a list of tests that you should actually apply in your PRNGs or TRNGs or random number generators to say that, okay, whether the tests are passed, and then this is whether it's recommended to be used in applications or not. And of course, if you run these tests, it fails, of course, by one of them because this is highly predictable. And usually the TRNGs are used for generation of the keys. Key are generated, or as I said, for during the protocol communication between two parties. Then some random numbers should be generated, and they should not be generated with very high speed and not very often. For example, after power up, the one random number is generated, and then afterwards it will be used for a long time. And then after some time, for example, every day or every, let's say, minute, then another random value should be generated as so. Or another one is to use the result of the TRNG as seed or nonce, and seed or nonce are what you usually use for PRNGs that we will see in one example. It means that the seed or the PRNG, because PRNGs are deterministic circuits, there is no randomness from them, but then you need to provide some inputs like seed, but then you need to let's say seed the PRNG, or the PRNG should be seeded, and this seed value should be random. Then you may ask, if I can provide a random value with data bit, why I should use PRNG? I mean, I just use the TRNG. But this is the point. The TRNG is slow. You generate the seed after power up, and then with a very high speed, you can generate a random stream with the PRNG. Now PRNGs, as I said, explain already the seed, usually generated by the TRNG, and then the stream that you generate, every state of the circuit, this is not a single bit, this is a state of the PRNG, is a function, or next state is a function over a few other previous states of the circuit. But then this function should be defined, and also to how many previous states the new state depends. For example, here we have S0 is 1, 2, 3, 4. This is the seed. And then we say the next one is always the previous one multiplied by this value plus this value, and modulo 2 to the 31 as an example. But most of the PRNGs have bad cryptographic properties. I mean, even if they pass NIST, they are not necessarily good, or they have good cryptographic properties to be used as a stream cipher. For example, here we have the cryptanalysis is a simple PRNG, the PRNG that we have just seen, the factor A Si plus B modulo M. Just imagine that you take two consecutive values here as two consecutive states. If you know two consecutive states of the PRNG, then you directly reveal actually A and B are as the coefficients, and then you can easily calculate the next state by knowing the state of the PRNG. This is the point now, the PRNGs, is that how many output bits of the PRNG you should see until you can know the entire state of the PRNG. And if you know the entire state of the PRNG, then you can generate by yourself the next state and next output of the PRNG. But cryptographically secure PRNGs, they are special PRNGs with some additional properties that the output must be unpredictable. Means that by knowing very, very long, even completely knowing the value or a state, knowing completely the output of the PRNG, this key stream, for very long, let's say 2 to the 32 bits, you should not be able to know the state of, or understand the state of the cipher or PRNG to generate the output or to predict the output with high probability. And this is what we exactly need as a stream cipher. I mean, if we have a PRNG which is cryptographically secure, this actually is something that we usually can use as a stream cipher. Good. And as an example, you may have heard of LFSR, linear feedback shift register. I guess you have seen it during the studies. That you have shift register, for example, here m bits that they are shifted from the left to the right, and then there is a feedback. It means that this is a shift register, but what is a new value? And the new value is a function over some of the previous values of the registers. You know? And then you get some of this as a feedback, and then XOR them, and then you provide the output. You know? Why XOR? Because it's a linear. Or why linear? Because all these functions are just linear, or just XOR. And then you see here the multiplication. This is actually an AND gate that you can make here, and then by this AND gate and this P are as a parameter, you can select which feedback function you build, or you can completely remove these AND gates and say there is a line here, or there is not a line here. Yeah, I mean this is exactly the same. And then maximum output length of PRNG, of this PRNG, of LFSR, is 2 to the m-1 maximum period. Means that after 2 to the m minus 1 output bits, exact the same sequence starts. The same sequence starts to be generated. Because of that, then the period of the LFSRs is actually limited. And then if you also don't know these feedback functions, there are actually works in that area. If you don't know this feedback function, then if you get 2m outputs of the PRNG, you completely can build that. Build the feedback function. Here one example, LFSR output is something like this, means that here there is no feedback, the parameter here. And then this is a super small PRNG or LFSR. And here, suppose that the seed is 1, 0, 0, 1, 0, 0, and the next state 1, 0 is shifted here, and the feedback is 0 because these two are 0, and the output of this will be also 0, then 0 will be saved here. And then you see here, the state is 1, 0, 0, and then we continue till here and say 7. State again is 1, 0, 0. Means that exactly afterwards, the same stream, if the output of the PRNG is this, exact the same sequence will be generated afterwards. Because it has 3 bits, LFSR, and then 2 to the 3 minus 1 is 7, then maximum period 7. But because you should consider this, by different feedback functions, you may generate a sequence which is shorter than 2 to the m minus 1. 2 to the m minus 1 is the maximum and depends on the size of the LFSR and also the feedback function. Good. This is what I already explained, that if you know 2m output bits of the LFSR of degree m, then the feedback coefficients, all these feedback coefficients can be calculated by solving a system of linear equations. I mean, this is out of scope of this lecture, but if you are interested, just search for it, you easily find it. And this feedback function is usually realized or shown by one polynomial, which is actually this PM. PM is now here. Is either they are 0 or 1, this AND gate, and then they actually explain whether you have a feedback or not. And this is exactly here that the coefficients of these terms of x to the m minus 1 or x to the m minus 2 till 0. Then because LFSRs are actually not cryptographically good enough, the combination of LFSRs and also NLFSRs are used. What is the NLFSR? It's a nonlinear feedback shift register. The combination of them are used to build the stream ciphers. These are the facts, sort of actually what I already explained, that the stream ciphers are less popular, and then block ciphers. In most domains like the internet and so on, I mean, they very rarely you see stream ciphers. The exception is RC4, which I'm not sure actually is used still, but might be in some protocols are still used. This is a stream ciphers, but you can of course use it as a block cipher. I mean, you can say every block I give to the stream cipher, and you wait enough number of clock cycles to encrypt or generate that key stream. And the stream ciphers sometimes require, most of the time, require few resources. Means that they are much smaller compared to block ciphers like the AES or DES or anything else. I mean, these stream ciphers, I mean, if even they are a combination of a couple of LFSRs, LFSRs are super simple to implement and super small to implement. But of course, they are slower compared to block ciphers. I mean, they can be slow. Requirements for a cryptographically secure pseudo-random number generator, or PRNG, are far more demanding than the requirements for PRNGs, which was used in other applications. This is what I already explained. This is a sum up. And single LFSR make poor stream ciphers, despite the good statistical properties. But if you combine LFSRs in a good way, you can build a strong stream ciphers. Here, we look at a Trivium. This is built based on 3 nonlinear LFSRs. This is one LFSR, you see A, B, C. And index are here 1 till 93, and here 1 till 84, and 1 till 111. They are different LFSRs, or non-LFSRs actually. And they are shifted every time to the right. Then how this works, look at here. What is the feedback function? 69 is taken and then XORed with something else and is fed in. And what is this? This is coming actually from here. And this is another non-LFSR, means that 66 is XORed with the output of this shift register, and it's actually coming here, and again XORed with the nonlinear function over 109 and 111 of this shift register, XORed again with the result, and this is actually coming back and building this. Means that these nonlinear LFSRs, they are not individual. They are connected to each other. This one updates, this one updates, this one, the other one updates, another one. This is complicated, and it cannot be easily evaluated or analyzed. But this went through a long competition, because there was a competition by, or let's say public competition about stream ciphers. Trivium was examined or analyzed by many researchers for a long time, and up to now there is no clear attack or let's say serious vulnerability of Trivium against different attacks. That they are known in the areas of symmetric cryptography and stream ciphers. And the output of this, you see the output of the key stream is generated from the output of this guy, and this guy, and then the XORed, and this is the bit. And then every clock cycle, you shift all of them and you generate 1 bit. And entirely is based on 288 registers and 3 AND gates, that you see here, 1, 2, 3, and some XOR gates. More information, how this works. And the length and the feedback of and feed-forward information of the cipher are explained here, but this works like this. The cipher has 80-bit key and also 80-bit IV, initialization vector. Then, for the initialization, we load 80-bit key into A here, and 80-bit IV to the B. You may say, hey, A has 93 bits and B has 84 bits. What I do with the rest, all other bits are 0. Means that from here, A, from 1 to 80, you fill it with the key. In B, from 1 to 80, you fill it with the IV, the rest with 0. And for the C, we fill everything with 0 except these three last bits, 109, 110, and 111, all of them we fill with 1. This is the load or initialization, and the warm-up is that clock, we need to run the cipher 1152 times without generating any output, means that this output should be discarded, should not be sent out. Now, if you send this out, you may actually leak information. Yeah, this should not be sent out. And then after 1152 times, then you are ready to say, okay, this output is ready to be used as key string. One more thing, even a smaller than Trivium is built with a lower security, which is called Bivium. If you are interested, you can search for that. Another thing is that, every clock cycle, this generates only 1 bit, no? But you can also unroll this implementation and generate more bits. No? I mean, this is something that you may consider. Yeah, that how you can unroll this. And unrolling means that you imagine that every clock cycle, instead of shifting 2 bits, you're shifting 1 bit, you're shifting 2 bits. Then you have to provide 2 output signals, 2 output feedback signals here, one for the LSB and another one for the bit after. Yeah, and then you need to build all these feedback functions as well. And then instead of generating 1 output bit per clock cycle, you generate 2 bits. But this can be actually generalized. Yeah? You can generate an arbitrary number of bits. But of course, the combinational circuit grows. Yeah? But the state of the cipher stays the same. Yeah? The size of the registers that you have. If you are interested, you look at all these links. No? The eStream project, which was the competition about the stream ciphers. And this is the official description of the Trivium, and there are a lot of programs and test vectors, C programs, and anything, everything that you can consider, you may think of. I already opened something for you. Here, Trivium. This is one of the links that you can set the key and also the IV and run it, yeah, and then you will see what the key stream is. Yeah. And I mean, some test vectors are also given here if you give this and this. And the cipher is also explained here in another language, I mean, compared to what I have explained. And here there is also a program here. The code that it gives you also information how this can be written, how it can be used. And even there is a C program, which I also provided in the Moodle for you if you want to see C++ implementation. And there is also a test vector in GitHub. Yeah, this is the key, for example, and this is the IV, and then it shows you, I mean, this can be generated. Yeah? And these are the official test vectors. You go to the end, this is the, I mean, that test vector that I showed had many zeros. And then here, for example, is fully random test vectors. I mean, if your implementation is working well, then it should actually work with this test vector as well. What you should consider is the order of the bits. You know, always when you implement a cipher, order of the bytes and order of the bits, both of them. I mean, you probably know little endian, big endian, and then how the test vectors are generated. I mean, the official test vectors, you know? Because anybody can build a C and say, hey, my implementation fits to that C, you know? I mean, of course, but it should actually fit to the official test vectors. And then, for example, the programs which are written, which generates or writes these test vectors, we should check whether what is the order of the bits, what is the order of the bytes. And if you build something, I mean, wrote a program or design for any cipher, and then you saw, I give such a random test vector at it, I can never find a problem, it never generates the correct output. I would recommend you always to fill everything with 0 at the start. You know, everything, key 0, IV 0, then you don't have any order. No order between the bits, no order between the bytes. And then you look at the output. If the output is correctly generated, or you see now the output is not correctly generated, and then you write the bits of the output that you generate and write the output of the test vector, and then find, okay, I actually swapped the bits, or no, I swapped actually the bytes. No? And then you find out if the cipher is fully working, but it doesn't work, it doesn't fit to the test vectors, then you need to find this way the correct order that you should provide. And then when everything works with all 0 inputs, no, and then the test vector is correct, then you test the other inputs and you see, again, it doesn't work. Because now that you mess up with the order of the input bits and order of the input bytes. And there you provide, and again, other test vectors, as small test vectors that only one bit is 1, for example, and to find out where the problem is. Now, as an example, we've seen an implementation of the Trivium, again on FPGA. Okay, good. What I have, let me explain the Trivium itself first. The Trivium what I built has clock, has reset, because you need to give the key and IV once and put the reset one clock cycle, then key and IV will be loaded inside. And then an enable signal, because in some clock cycles you don't want to generate the output, you know? And one ready signal, which is actually given by the Trivium out. Means that after the reset, you wait till the ready is 1, means that the initialization is accomplished. Then you can make the enable signal 1 and then read from this out. Means that as out you can read, but with the enable you generate the other output, which is a single bit. And then what is important here, I try to keep this constant or consistent with what I have shown in the slides. Means that here, because the left side is 1 and the right side is 93, and then I actually try to do the same for the IV and the key. Then I have one shift register as a component, which has the clock, of course. It has enable signal to shift, and also another input as parallel or parallel in. This means we need a shift register. I mean, either left to right, I don't know, I mean, at the moment, but suppose that, for example, we shift from left to right, but then bit by bit we shift if the enable is 1. And then at the same time, we have the option to load parallel. Yeah? Then if, for example, this is n bit, and we give here 1 bit, then serial in, and here is parallel in. Then with enable signal, of course, we have one enable and one parallel input, no? as a signal. With a parallel input, this signal, we define whether we want to shift serially or we want to load in parallel. Why we need that? Because when you need to load key and IV in one clock cycle as the init into the registers of the Trivium, then you cannot actually do it bit by bit. No? Otherwise, you need to wait 80 cycles. Then this is built, no? The shift register, which is actually nothing particular, but here clock enable parallel serial in and parallel in, and then if the clock is positive and enable is 1, then we look at the parallel. This flag is 1, then we say the state of the register should be parallel in. Otherwise, we are shifting from left to right with the serial in, which is given as the primary input, and the state, which is 1 to size -1. You know, we shift like this. Good. Then we have this shift register, the counter exactly as the same as we have seen before, and now a bit of signals. I mean, I will explain them later. We have register A for here, register A. You know, this register, and another one for B, another one for C. And you see here, register A, 93, register B, 84, and register C, 111. And each of them has one flag. Yeah, register enable, register parallel. Keep in your mind here that all of them are sharing the same enable and a parallel because either all of them are shifted from left to right or all of them load in parallel. But of course, their serial in and parallel in are different, and the output of the register, what I have defined is just a completely parallel output. Yeah? Means that this one has 93 bits, and this one has 84 bits, and the other 111 bits. Now, the counter is also okay. I mean, I defined the counter 11 bits because, as if you remember, we require to wait 1152. That for that we need minimum 11 bits. I don't know, 11 or 10, 1024 is not enough. Yeah, 11 bits we need. And now the parallel inputs are for the initialization. I just defined the key that we received plus 0 and IV concatenated with 0. And if again you remember, this was all 0 and then 3 times 1. Yeah, that they are loaded here. Here, all 11 and the rest is 0. This one. This is the parallel input. And now I need to, or we need to actually define here. You know? Each of these XORs and AND gates, each of these XOR gates and AND gates need to be defined, and you need to define a signal name for them. And what you see here is just a combination circuit by that. You know? For example, register 866, register A93 XOR, and it's called register AT. Here, 66, yeah, coming here, and 93, the last one, you know, this XOR. Then we call this value something. But then I don't go to all the details, yeah, because this is just building this XOR and AND gates. And S out is the XOR of all these bits. And they are the serial inputs, yeah, which if you look is the XOR, 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 and the AND, exactly similar to the figure that you have seen. Yeah, the combinational circuit is easy, but you need to build the controller. Yeah, the controller is more important. Default values, you know, that the counter and the enable, counter reset and counter enable are all 0, and then you need to set them, you know, in different states. And then here what we do, if reset is 1, yeah, if reset is 1, then we say that the counter reset should be 1 because we need to wait. Then afterwards 1152. And then we say that the parallel flag is 1, means that we need to load in parallel, and the enable of all registers is also 1. Yeah? Then if the reset signal is 1, then we set this, clock comes, everything is parallel loaded, and then the counter counts, because we say here counter should be enabled, as long as the counter value is smaller than 1152. Yeah? And then easily, instead of writing the binary value, I just convert it to integer and then just write it here. Yeah? You can also do that. Once we receive 1152, then we stop the counter, because then counter enable is not 1 anymore, because the default value is 0. Yeah? When we are here, and then we set the enable signal 1. We set the ready signal 1, means that we tell the outside the ready signal is 1. And the register enables become actually the enable. Yeah? You don't need to write a 0 or 1. Yeah? The enable signal that we gave as the primary input here, this you connect it to now the enable of the registers. And if the enable is 1, the registers are clocked serially. If the enable is 0, it stops. That's the Trivium. Then how to use it here? What I have defined the register inputs, which is long, yeah, which is key plus IV, because I want to send from outside through the UART key and IV. And you see the order, I'm sending it from this order. Yeah. And the output is also shift register. And And interestingly here, you see, I don't have a long shift register. The shift register is there, but it's shifted 1 bit per cycle because the output of the Trivium is 1 bit. But now you see the output of the Trivium is taken and now shifted in this way from left to right. And then the controller should wait 8 clock cycles till this register is filled with 8 bits of the Trivium output, and then stop the Trivium, send it outside through the UART, and do the same again. Yeah? And the rest you see here, the Trivium is Trivium reset, Trivium enable, register input. This part, as I said, that you send from the UART, from outside the key and the IV, and then this signals Trivium ready, Trivium ready, and Trivium S out, which is actually used here. Yeah. Now what we need to think about is how to control. Then controller, as I said, it generates enable and reset signal for Trivium, and it also observes whether the Trivium is ready. It means that the initialization phase is complete. Again, I need a counter, but 2 counters I need. Why? 1 counter I need for bits when I generate the output, because every 8 bits I have to then wait, then send it outside. But how many of these bytes I'm sending outside? I decided based on the test vector, the 64 bytes, for example, this long. Yeah, this is my choice. Yeah, I mean, I decided, okay, 64 bytes. And then I need a counter to count from 0 to 64. I also need a counter to count from 0 to 7. Yeah, and I cannot actually mix them because one of them you need to wait 8 times, and then each times you have 8 bits, then you need to wait again or repeat this 64 times. Good. Then these flags, as before, save in and save out, they're coming values and sending out signals for the registers through the UART. They are default 0, and this is as before UART. Now counters are all completely 0, 0. Yeah, enable and reset are 0, both of them, and the Trivium as well. Yeah, Trivium is not enabled, and reset is also 0 by default. Now, when we receive data, we receive as long as we receive actually 20 bytes, right? Is it 20 bytes? Yes. I think 80 bits for the key and 80 bits for the IV. No? In total, you have 20 bytes to receive. Then we wait till 20 bytes are received in the order that I just shown you. And then afterwards, when we receive 20 bytes, in 1 clock cycle, Trivium is reset, and then we go to the wait, and we wait here till Trivium ready is 1. When Trivium ready signal is 1, then we know that everything is ready, but we did not enable the Trivium, means that it will be ready and it waits. And then we reset both counters, and here we start generating the output and sending it to output, through the UART. We enable the Trivium. Save out was the signal to save shift register bit by bit to that 8-bit register. And then we enable the first counter, the counter which comes from 0 to 7. And once we have to 7, we say, okay, 1 byte is ready, send it out. This sends it out. And then it goes to the next. In the next, the counter will be enabled once only, and it checks whether we reached 63 or not. If we reached, then go back to the idly. Otherwise, reset the first counter, which is important. Now, reset the first counter, which comes from 0 to 7, and then go to the next state to run the Trivium. No? Is it okay? No? I mean, the Trivium by itself, if you look, is easy. Implementation is also easy. Yeah, but if you integrate it into some other framework to read and write and put the value somewhere and the order, this becomes important. Now I try to generate a bit stream and then show you the things on the FPGA. This is now done. And I think I don't have the FPGA connected. Now, what was the thing? We wanted to send the key and IV. And which one? The first one? Here, we were shifting UART from here to here, and then we need to first send the key and then the IV. Now, edge term, disconnect, connect, clear. Now, one of the test vectors, that was Trivium. This is the key. Then this is the key, and this is the IV. Then okay. Yeah, you see A4338, C's blah blah till 1F. Yeah, and this long sequence we have provided using the Trivium. Yeah. Of course, you can check the other test vectors if you want, or look at the implementation and then make yourself familiar with the implementation and also Trivium.